My next topic that I want us to consider is what happens with the heart function relative to input from the autonomic system. You know we have two parts of the autonomic system, parasympathetic and sympathetic. You also know that the sympathetic is going to be increasing the heart rate. It will increase the force of contraction of the heart, leading to overall increase in cardiac output. You also know that the parasympathetic input to the heart, which is mediated by one of the branches of the vagus nerve, the 10th cranial nerve, will have sort of opposite effects in the sense that it is going to cause the heart rate to slow down. It doesn't have as much of an effect in terms of the power of contraction that the sympathetic does. So the sympathetic and parasympathetic are not exactly mirror images of each other. Certainly one will increase the heart rate, the other will decrease the heart rate, but the sympathetics will have a significant effect on the force of contraction, where the parasympathetics not particularly. So one of the other points that I want you to understand is that, as we've said earlier, the generation of the beating of the heart itself is completely autonomous. It doesn't need any neurological input to beat. So the beating originates within the heart. And of course, the main place is going to be the SA node. And we've already talked about all that business. But one of the things you're going to want to remember or to consider is that you always have autonomic input to the heart. So it's not like you have no sympathetic input to the heart until you start exercising or until you start becoming fearful or something that would affect a sympathetic event. You have a baseline sympathetic input to the heart. And as you already know, the neurotransmitter associated with the sympathetic is going to be norepinephrine, and of course the adrenal glands, if they get involved, it'll be epinephrine. So you always have a baseline of sympathetic signal to the heart. So even if you're sitting calmly in your chair, you still have a baseline level of that. You always have input from the vagus nerve. You always have input of sympathetic to the heart. And it's trying to slow the heart down. Your sympathetic's trying to speed the heart up. So you can view them, one as an accelerator and the other as a brake pedal. So I have both of those coming into the heart at the same time, a basal level, regardless of what you happen to be doing at the moment, and they're pushing against each other. So I am gently pushing the accelerator and the brake at the same time. Now, in medical speak, we say that we have an autonomic tone. You have a sympathetic tone to the heart. You have a parasympathetic tone to the heart. So they're pushing against each other. So if you can go with the analogy of I'm gently pushing on the brake, and I'm also gently pushing on the accelerator, then what if I were to pull off the brake, not change the accelerator, I still have a positive effect in terms of increase in heart rate, yes? And I didn't do anything to the sympathetic tone. I just backed off the parasympathetic. Or I could not mess with the brake and then alter the accelerator. I don't know if I said that correctly or not, what I just said. So let me go back and say that again. The accelerator is going to be your sympathetic. Your brake is going to be your parasympathetic. So again, if I hold one steady but back off the other, I'm going to have the desired effect of what you would expect. So all that to say, if you alter one or the other, you're going to be altering the activity of the heart, but they're always there. So I guess a more specific example would be, again, your heart is beating. You have your sympathetic tone coming in, you have your parasympathetic tone coming in, and then for whatever reason, you have an increase in your vagal tone, an increase in your parasympathetic tone. You haven't altered the sympathetics, but you have a increase in the parasympathetics from the vagus, and now you're having a neurotransmitters being released, and the neurotransmitters, acetylcholine, which is going to be your parasympathetics, is causing the heart to slow down. Now, the sympathetics haven't changed, but if you have an increase, a significant increase in your vagal tone, then you're going to get lightheaded and possibly pass out. And that is what one of the things we call that is vasovagal syncope. So increase in vagus tone slows the heart down, decrease in cardiac output, drop in pressure, and now you're lightheaded and possibly will pass out. So again, what I did there is that I tapped on the brakes, but I didn't move the accelerator. And so slowing the heart down. So you have this interplay, okay? All right, so let's kind of get down into what's going on with all of that. So we're going to take sympathetic as being our launching point. So this should be a familiar diagram. So this is going to be kind of a cartoon illustrating the typical undulating pattern for these pacemaking cells. And we're just going to assume this is for, say, SA node. Okay. And so here's your undulating pattern, and here are the various channels at play. And this particular diagram here, as we did in an earlier diagram, he has it labeled IH, and that really is IF, as in funny channels. So I'm having my funny channels here, and of course you know that the sodium is dripping in with the funny channels. Okay, ever raising the membrane potential. This is, by the way, we're going to consider this to be baseline here. That would be normal. So we have that going on. And then, of course, we hit the threshold for the T-channel calcium. And then that's going to bring also, quickly following that will be my L calcium. And so I'm going to have a depolarization. Note it doesn't get very high. And then those close, and then I'm going to have my potassium channels are going to open. And I'm not going to rehash all the potassium channels. You can go back to earlier lecture for that. And then the potassium is going to be flowing out in excess of the calcium flowing in because they're closing. And then I'm down back towards repolarization, and then get to do it all over again when the potassium channels close down. Then I'm back to my set point again. So you have that undulation pattern over and over. Well, when you have a sympathetic event, and that's going to involve epinephrine, norepinephrine, they're going to be binding to the receptors, and the main receptor is going to be a beta-1 adrenergic receptor. That's going to be the main receptor as far as heart tissue is concerned. You do have some beta-2s there, but they're kind of minor role. So a big player is beta-1. So you're going to have your norepinephrine and your epinephrine binding to beta-1 adrenergic receptors. It's going to kick up the cyclic AMP, and then again, cell biology happens at this point. As you know, the cyclic AMP can lead to a variety of cellular changes. Things may get phosphorylated, dephosphorylated, etc. So what's going to happen when you have an elevated cyclic AMP? Multiple things happen because you have many of the regulating points are going to be altered because of cell biology. So one of the things that's going to happen is going to be affecting the funny channels. And so now the funny channels are going to be a little more generous in terms of allowing sodium in. And so what you're going to get then is just something happening a bit quicker. And so now here is going to be my sympathetic side of things, where through cell biology, my funny channels are now more liberal in terms of allowing more sodium in per unit time. So I'm going to have a quicker ascending phase to get to that threshold for the T calciums. And of course, they're going to open up more rapidly, okay, because again of the effect on the funny channels here. So you have that going on. And then also you're going to have an opening, or the voltage-sensitive sodium channel, voltage-sensitive potassium channels are also going to be influenced as well, again, by cell biology. So now they're going to open up more quickly and allow more generous amounts of potassium to leak out of the cell. And so the end result of all this is that things happen more rapidly, you see. This is oversimplification because probably the calcium channels are also affected by cellular processes in response to the norepinephrine and the epinephrine. So that's going to happen. Of course, the theme here is that everything happens more rapidly. Another thing that happens as well is that these potassium channels open up, allowing more efficient potassiums to efflux, and then they're going to close, and you'll note that they close, they don't get quite back down to the negative level that they were normally. So what does that mean? What that means then is that it's a shorter amount of time then to get to the threshold of the calcium T channel. So you have a little bit of a shift in terms of where you're bottoming out as well. So all of these things point to the same direction of basically having a quicker flow of the sodium coming in, the calcium coming in, and then the potassium leaving. So it ramps everything up. Many other processes also are affected by the binding of norepinephrine, epinephrine to these beta-1s. You're going to get a kick up on the activity of your sodium-calcium exchange pump, so it's going to be spinning faster. Again, it makes sense because I'm getting more calcium in, I'm getting more sodium in and such, so it's got to be doing its thing more quickly. In fact, all the pumps involved, typically because of a various cell biology downstream effect from that initial binding of norepinephrine and epinephrine to the beta-1s, is going to be causing everything to happen very quickly. So what you get then is this pacing, a rapid pacing or a quicker pacing of what's going on with the SA node, and then of course if it's firing more rapidly, then everything else is happening more rapidly as well. So that's kind of the pacing of things. As far as the force or the stronger contraction, the sympathetic system will cause, again, a more forceful contraction of the heart, so we would call this a positive inotropy or inotropic effect. So it'll be positive inotropy. And so inotropy is a medical term for force of contraction. So if I have a positive inotropic effect, that means I'm having a more forceful contraction. If I have a negative inotropic effect, that means I'm having a weakening of the contraction or less force of the contraction. So we just saw last time how important the calcium is in terms of getting in there and causing the actin and the myosin to interact and such. So what's going on with that? Again, norepinephrine, epinephrine binding to the beta-1s. Again, beta-2 minor role. Increases force of contraction. Multiple mechanisms at play here. One of the mechanisms is you're going to have more calcium flowing in. So we're going to have an increased opening of these L-type calcium channels. So more calcium flowing in means then I'm going to have a more forceful contraction as you think about the calcium interacting with the myosin and the acting and the rationing business. This, through a series of cellular biological processes, you're going to have increased RYR2 receptor as well. So things are going to happen more rapidly there. So again, generating more calcium coming into the cell. You're going to have a ramp up of that circa 2 pump. It's going to be spinning more rapidly. You remember that's an ATPase pump, circa type 2. So I'm going to have that going on. So the overall feel here is I'm going to be delivering more calcium into the cell, and that's going to accelerate the force of contraction, of course. Now, the increase of force of contraction is not, the main one is that you have an increase in calcium, for sure, but it's not exclusively that way as well. There are other cellular processes that can affect the actin and the myosin. Such that it makes it work more efficiently. You can actually have cellular processes that will cause the affinity for the myosin for the calcium to increase. So these cellular processes can actually influence myosin. And so that would be yet another way of having a positive inotropic effect. Again, that's just an example. So my point is that the main mechanism for an increased force of contraction is going to be more calcium, but there are other cellular processes, such again, that can alter the nature of the actin and the myosin that could cause a more forceful contraction. And then, of course, if we're doing that, we also have to accelerate everything else, because if we're dumping more calcium in, we have to be better at getting the calcium out. So all these various pumps are also being affected and acting more efficiently in response to that as well. Okay, so that's it for the sympathetics. So we'll take a look at the parasympathetics in the next block.